Hello and welcome back. In this video we'll be looking at parts of section 2.4 and 2.5 on applications specifically of right triangles, meaning that we're looking at acute angles. So remember that in a right triangle, if we have one right angle, the other two angles must be acute angles. So when we're looking at sines and cosines, we're really only looking at acute angles in this section. So given enough information about a right triangle, we can normally solve the rest. So there's a couple of useful formulae that we use to solve all sorts of information. And before I write this down, I just want to note that it is very common to label the sides and the angles of a triangle using A, B, and C. So for instance, this angle down here, which we'll call the angle A, the side opposite of the angle, the one that is not adjacent, either on the left or right, we will normally call lowercase a. So we use capital letters for the angles, lowercase letters for the sides. B and B are always across from each other. C and C are always across from each other. And normally, C, if there is a right angle, C is normally the right angle. This isn't always the case, but if nothing is said and we know that it's a right angle triangle, normally we will assume that C is the right angle. So the first thing is that we have Pythagorean Theorem, which is going to be that a squared plus b squared is going to be equal to c squared. This is useful. This only applies to right triangles, but right triangles show up so much that this is a very, very useful formula. And then likewise, we have the sine, cosine, and tangent of this angle. Now let's look at A. So sine, when we're dealing with a triangle, we can think about SOHCAHTOA. So sine is going to be the opposite over the hypotenuse. So the SO part, the opposite is A over the hypotenuse. Ka, so AH is going to be the adjacent, which is B, over the hypotenuse, which is C. And tangent, which is going to be opposite over adjacent, the TOA part. So these are realistically going to be the only formula that we'll use to solve things about right triangles. In this section, they're just so useful we don't need anything else really. So for instance, here we've got a triangle. We've labeled some of the angles with what we know they are. So for instance, this angle down here is going to be 20, we're told. This side length is going to be 5. And we want to figure out the rest. Well, we're told that this is a right angle, so that's 90 degrees, which means that we should be able to figure out A, because the angles in a triangle should add up to 180. So for instance, if I took the angle A plus 20 degrees plus 90 degrees, that should be equal to 180 degrees. And then if I solve this for A, I just subtract 90 and 20 from this side, and I should get that A is 70 degrees. Nice. So now I need to figure out A and C. So I need to use one of these angles. I might as well use this 20-degree angle down here to solve for A and C. So 5 is going to be the opposite side of this 20. So I need a relationship that relates, say if I want to know A, I need a relationship that relates the opposite to the adjacent. Well, opposite and adjacent, that should be tangent. So 10 of 20 degrees should be the opposite, which is 5 divided by A. And if I solve this for A, I'll say like I multiply both sides by A and divide both sides by tangent. We see that A is going to be 5 divided by the tangent of 20 degrees. And I can solve for this. So here, tangent of 20 degrees, this is not a special angle, so this is not one that I know off the top of my head, but we can use a calculator. I like the online calculator Desmos. This is just, if you Google Desmos, this nice scientific calculator will show up, and we want to make sure that this is working in degrees, but I can take 5 divided by the tangent of 20, close my parentheses, and we can see that we have 5 divided by the tangent of 20, and when we hit enter, we get 13.7373871. I'll just round this to 2 decimal places. So this will be 13.34. So 74. And so now we know A, we know 2 sides, and we can get the third side either by using Pythagorean Theorem. So for instance, I know that 5 squared plus A squared, which is going to be this 13.74 squared, should be equal to C squared. So I can solve for that using this number, or I can solve for it in another way as well. So we've got more than one way to do this. This 20-degree angle, I can relate 5 to C as well. 5 is the opposite. C is the hypotenuse. Opposite over hypotenuse is the sine. So if I take the sine of a 20-degree angle, that should be opposite over opposite over hypotenuse, excuse me. If I solve for C, I can multiply both sides by C, divide both sides by 20. I get that C is 5 over sine of 20 degrees. And again, I can plug this into my online calculator. 5 divided by the sine of 20, and that will equal 14.6. If I round that to 2 decimal places, 62. 14.62. And if I were to plug this in over here, we should get that this makes a good equation. So let's try that. So let's try 5 squared plus 13.74 squared. So 5 squared plus 13.74 squared. And we get 213.7876. And if I come back and I take C and I square it, so that's 14.64 squared. 62 squared. I get 213.7444. And these are close enough that they're probably off because I rounded. If I'd used the exact values, I would notice that they would be exactly the same. So everything checks out.